the end of the week. Right. Morning, how are you guys? Okay, thanks for letting me know.
Said he was sleeping.
Is that okay? Oh, we're already on. Okay, great. We're live. Right when John walks in, we're live.
Party has arrived.
All right. Okay, so I promised Rebecca that we discuss the final exam today. The date, right? Okay, so let me write some things on the board. So the two last things in the class before, besides the homework, and let's see, there'll probably be two more homeworks, is the final exam and the project. And normally I make the project due like the last day of class and the final exam during the normal final exam. But I talked at the beginning of the semester about switching those, and I'm happy to do that, right? So basically we have to discuss due date for the Monte Carlo project. It's called Icing Model Project. And then the final exam date. Okay, and here's our choices. So the date we have allocated for our final exam is Thursday, December 3rd. Okay, and of course that's after our last day of class is before Thanksgiving. So that's one option. And I've said we can move it. Our last day of class is Tuesday, November 24th. Okay. Okay. And I think the earliest I want to give the final is the Thursday before that. Thursday, November 19th. I don't really want to give it before that. So these are our options. Now technically, this is the last day I'm supposed to give exams before finals week. Technically. But because this is a final exam, I think that's fine. Right? So technically I think I can give the final here. I just can't give an exam before the final here. And so I'm happy to move these around. I'm happy to, if people want to take the final before Thanksgiving, I'm happy to do it somewhere around here, and I'm happy to make the icing model due here. Or we could do vice versa. Any preference?
I think I'd probably prefer to take the exam before Thanksgiving.
Yeah, that's what we thought. That's what we talked about before. So what about this day?
Do you know when we have quantum? I was just trying to look at this syllabus and stuff like that.
The second test is November 3rd or something like that, and then we'll have a final during finals week.
During finals week.
Cool.
This is nice because probably there's no other exams this week. Unless someone's doing the same thing I'm doing.
Yeah, I don't think so.
So this gives you a week, and then you get done before Thanksgiving.
Yeah.
So then, that's nice.
Yeah.
And then you can just have fun with Python programming and everything.
You'll be available for helping us.
Yeah, no, so that's right. So that's a nice thing is basically for this, we can schedule some office hours just some like Blue Jean sessions.
Workshops.
Yeah.
Right? And so that would be more fun anyway.
Yeah.
Because we could just talk about Python.
Yeah.
Yeah.
Great.
So you guys want to do that?
Yeah, that
Yeah.
sounds great.
So final on here?
Sure.
Is that okay with everyone?
Yeah.
Yeah? Okay. I'll send out an email and, check your calendars, make sure, and let me know by, next week if it's not going to work. So basically, tentatively, we'll do this. This will be our final. And I'll send an email.
What time block?
Probably just normal class time. Same as the midterm.
Oh, it's that short? Okay, cool.
It would just be the same as midterm.
Okay.
Same as the midterm.
Very cool. It's normally for finals, they block off like.
No, I'm not. I don't like. I won't. I would never give a test more than 2 hours. Right? That's just cruel. Right? So the midterm was 2 hours. The final will be 2 hours. It'll be the same length test. Okay, and then here will be your. How much time does that give you?
At least 2 weeks. If you get, it depends on when you give us the project.
Well, I mean, suppose. I mean, I'm happy to make it do later than this.
Yeah, I mean, if you want to make it.
At the end of
That's fine, yeah.
finals week.
December 11th.
Let's.
Yeah.
10th,
10th, yeah, I think.
December 10th, yeah. And then your last day finals is Thursday.
Yeah, I'm happy to do that because basically, if you're studying for your exam, you're not gonna work on this, and then I want to go to Thanksgiving, and so then after Thanksgiving, you're already in December, and that's only like 3 days.
Yeah.
Okay, so when's the last day of finals week?
Thursday, December 10th, usually, and then the 11th is a like makeup day.
So let's do that.
Yeah.
How about that?
Sounds good.
Okay, so I'll send an email, and that sounds like a good plan to me. So Tuesday the 24th will be the final, and then the last day, because obviously I need to get grades in, but if I make it do the last day of finals week, that gives me time to get grades in. So Thursday, December 10th. Yeah, because our final is basically the earliest side of finals, like either the first or the second day of finals. Thursday, December 10th is the project. Okay, great. I'm glad we decided on that. Cool. So, I know you guys were working hard on the homework. This is on, right? So I'm not going to give you a problem set today. You have a break this weekend. Is that good, John? Am I good?
Yes, you are.
Okay. So I'll give you your next problem set next Tuesday. That would be problem set 6. And you'll likely have probably problem set 6 and a problem set 7. Okay, so my only announcements are the problem set 5 is due today. You guys all know that. So due today. Because I'm not giving you a problem set, it's a good opportunity to catch up with reading. Okay, so we finished our discussion of gases. So try to finish reading Macquarie chapter 6. Because we're done with that. Macquarie chapter 6. And we're going to start something new today. We're going to start phonons, and that's Macquarie chapter 11. So we're skipping a few chapters. And we're going to start today with Macquarie chapter 11. Okay, so that's where we are in the book. Is this marked down? Yeah, let's use this marker. So we're gonna start something new today. Exciting. We're gonna start phonons. Let's get my notes. Okay. John, can you check me over here? Is this fine?
I cannot see you.
Here?
You're good right there, yeah.
Okay, great. Okay, so today we're gonna start phonons. This is crystals. So we're gonna start monatomic crystals. Why? Well, we finished gases. Okay, and we're gonna focus on phonons in the crystals. We also need to worry about the electrons. Unfortunately, we may not have time to talk about the Fermi gas, which is how you treat the electrons. We're going to focus on phonons, and we're going to focus on reproducing experimental heat capacities of phonons on heat capacity, because we can directly compare to experiment. Okay? And so why are we moving on to crystals? Well, because we just finished gases, okay, we have finished gases. We've learned all the statistical mechanics of monatomic, diatomic gases. You can look in Macquarie. Polyatomic gases, polyatomic molecules, are very similar. You just need to do the vibrations, essentially how we do phonons. So actually talking about phonons tells you how you would do polyatomic molecules. You switch to normal mode representation, which is exactly what we can do. So essentially we're done with gases. So next options would be other phases of matter, right? Either crystals, liquids, or amorphous solids. Okay, so those are our options once we're done with the gases, and these are hard, right? Liquids and amorphous solids are hard, and so the reason we're doing crystals next is because they're the easiest. So we're starting with things that are easier. So that's why we're going to do crystals, and so let's think about our goal. So our goal is going to be to derive expressions for the heat capacity that agree with experimental measurements. Okay, so our goal is derive following we're going to care about low temperature and high temperature behavior of the heat capacity. Okay, and so at low temperature, what we're going to want to prove is we're going to want to prove that the heat capacity goes like this. CV, we care about C, right? Crystals aren't expanding, the volume's essentially constant, so we can just focus on CV. It's going to be a function of temperature. And we want to prove that it goes like this at low temperatures. It has one term which is proportional to T. I'm going to say it's gamma T. Gamma is just a proportionality constant. And we have another term that's proportional to T cubed. So the T cubed term dominates. It turns out that this term is due to the electrons. And this term is due to the phonons. Do people have an idea of what a phonon is? Okay, good, we'll see that today. We'll define what a phonon is today, mathematically, and I hope you like the definition. Phonons are just vibrations, crystal vibrations. We'll define them today. This term dominates this term. We can derive both of them. Unfortunately, we're not going to have time to do this probably, so we're going to focus on this. Okay, so we want to show this behavior, the T cubed behavior. At high temperature, we want to prove this behavior. CV of T at high temperature goes as 3 NkB. It's independent of temperature. Okay, this looks like equipartition. Remember, we spent a lot of time last class talking about equipartition. This looks a lot like equipartition. This is called the law of Dulong and Petit. Okay, so it was experimentally observed, and it was given a name. It's called the law of Dulong and Petit, the heat capacity of phonons at high temperature. Okay, now why is this important? Well, this was one of, when you take quantum mechanics, and maybe the first day of class, Mark Cicerone tells you the motivation for quantum mechanics, all the early experiments for why classical mechanics fails. You talk about the double slit experiment, you talk about Bohr's model of an atom, you talk about blackbody radiation. This is another one, actually, that you don't really talk about that often, but people were trying to understand these heat capacities back in the early 1900s. And Debye and Einstein were working on this in like 1910. 1910 is before quantum mechanics, right? Quantum mechanics was like 1928 through 1930, right? And so it turns out you can't reproduce this with classical mechanics. And so this was one of the other early experiments that suggested the need for quantum mechanics. And so if we can prove this using quantum statistical mechanics, it's one of the earliest experimental validations of quantum mechanics. All right, so let me just write that down. So low temperature behavior cannot be explained by classical mechanics. Okay. And so this means getting it right was an early success of, what do you want to call it? Pre-quantum mechanics. You know, just like black body radiation, Planck didn't exactly know quantum mechanics, but he knew something about quantization. So it's an early success of, you know, the pre-development of quantum mechanics. So getting it right was let's say an early success. Let's just call it quantization theories. Maybe we don't exactly know. Well, now we exactly know quantum mechanics, but back in 1910 they didn't. But they did propose a quantization theory that can get it right. Okay, so that's why we care. Okay, I have a picture that normally I would hand this out to everyone. I'll post this on Canvas. Can everyone see this? So this is an experimental measurement. This is on copper. And this is what it looks like. So here's the temperature, here's the capacity. Up here, I'm at 3 nkb, and here's my low temperature limit. And so what we're going to try to do is reproduce something that looks like this. We're going to try to reproduce this limit and this limit. Okay, so I'll send this handout. I'll post this to Canvas, and we'll talk about it more when we're done deriving it. So that's our goal. Okay, so how are we going to do it? So everyone happy with this goal? Everyone agree with me this is an important thing to do, hopefully? Okay. So I want to draw a picture that I don't want to erase, well, at least for a while. So we need to describe phonons in crystals. Okay? And surprise, surprise, today is going to be a lot of matrix algebra. Surprisingly, we haven't done much matrix algebra in this class. Has everyone taken a matrix algebra class or a linear algebra class? Okay, good. We're going to use a lot of matrix algebra today. So hopefully that's fun. Let's paint a picture of a crystal. What does a crystal look like? Okay? I brought colored markers for this.
Thank you. Important.
Expo brand too, of course.
Yeah. Okay, let's draw a picture of a crystal. First thing we're going to draw is a lattice. These are not the atoms, these are the lattice sites. And if I was better, I'd make them equally spaced. Okay, so we draw a lattice. Okay, pretend that's a really nice lattice. Okay, so these are not the atoms, these are the lattice sites. Okay? Right, so we have some notion that a crystal, the atoms are periodically arranged, but they're not going to be perfectly periodically arranged because of you have finite temperature. Okay, and so this is, you can think about this as the average position of the atoms, or the equilibrium position of the atoms. Okay? Rigorously what it is the position of the atoms at 0 Kelvin, when you have no kinetic energy, right? Position of atoms at 0 Kelvin if they're not allowed to move around. Okay? But the atoms are moving around. So now we're going to draw my atoms in black. Okay, and here's my atoms. They have to be close to the orange sites, and we're going to put them on springs. Okay? Like that. Right? Okay, I don't want to draw all of them. Okay, you get the point? It looks like Halloween, right? These are my atoms in black. Atoms, atom positions at t greater than 0K, right? If they have some energy, they're off their lattice sites. They're not off by much, so this is an exaggeration, right? I've really exaggerated because this guy isn't off its lattice site by that amount. Okay, so I'm exaggerating it. The springs indicate that there's some restoring force, right? There's a restoring force back to the lattice sites. The restoring force is essentially the electronic energy of the system. If they're off the lattice sites, then they're not in the most stable position. Okay, so that's how you want to think about it. And we're gonna define different variables here. So this is the last time I'm going to use orange. So define the lattice site positions by, okay, lattice site positions are denoted, I'm going to say it's x1 naught, y1 naught, z1 naught, x2 naught, y2 naught, z2 naught, dot, dot, dot. Right, so naught means it's an equilibrium position. Okay, and this is just the Cartesian coordinates of my first atom, Cartesian coordinates of the second atom. These are the lattice positions. My atom positions I'm going to define the same way, except I'm not going to use the naught. Okay, so atom positions. Did I just switch back to my beta marker? Yes. Atom positions. Same thing, except I'm not going to use the naught. x1, y1, z1, x2, y2, z2, dot, dot, dot. Okay? So, okay, that makes sense to everyone? So now what we're going to do is what we know where the lattice is, presumably. You know, we can do X-ray diffraction, we can figure out where the lattice is. So that's not the question. The question is, where are the atoms, right? We know where the lattice is, so we're wasting information if we use these coordinates. The simplest thing we can do is use relative coordinates, right? Because if we know where the lattice is, then the relative coordinates tell us where the atoms are relative to the lattice site, right? So that's the most straightforward variable to use. So what we're going to do is we're going to find relative coordinates. And there's going to be 3 n of them. N atoms, 3 Cartesian coordinates for each atom. And so what the relative coordinates are is they tell me where the atom is relative to the lattice site. Okay, and I'm going to use a variable c to label these relative coordinates, just like the partition function except lowercase c. So we're going to call C1, Greek C. This is the relative displacement x for atom 1 away from its lattice site. So this is x1 minus x1 naught. Okay? And what I'm going to do is I'm going to group all the x, y, and z together. So C2 is not a coordinate for atom 2, it's the y coordinate for atom 1. Okay, so it's y1 minus y1 naught. C3 is a z coordinate for atom 1. And when I get to C4, I get to the second atom, x2, minus x2 naught, dot, 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 and I have n atoms, 3 Cartesian coordinates, so I have 3n of these, right? So C3n is Zn minus Zn naught, okay? So just defining relative coordinates. Everyone okay with that? Yeah? Okay. So the key thing is the energy of the system depends on the relative coordinates, okay? So we need to construct our Hamiltonian, so we need the potential energy. The total potential energy of the system can be written in terms of these relative coordinates. Okay, and so I can write it as U. I'm going to use U for the potential. U is a function of all of these relative coordinates. C1, C2, dot, 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 C3. Okay? Now here's where the matrix algebra is going to come in. I don't want to have to write my 3n c coordinates all the time, so I'm going to put them in a vector. Okay, so I'm going to put them all in a vector, and it's going to make keeping track of them easier. And so once we have vectors, we have matrix algebra, right? So what we're going to do is we're going to define a column vector to keep track of all these things. Okay? And so I'm going to have a vector of these coordinates, C vector, and all it's going to be is just a column vector that collects all these coordinates. And C1 is up here, C2 is down here, dot, 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 C3n. Okay? So I'm just collecting all the coordinates in a vector. Okay, right. So now what we're going to do is, these things are large or small?
Small.
Small, right? By construction, they're small because we said that atoms are near the lattice. So these things are small. When all of these are 0, what happens?
We're at 0 Kelvin.
Yeah, all the atoms are on the lattice.
Yeah.
Okay, and so that's going to be our reference energy. So assume either we can just use that a reference energy for all the atoms on the lattice. The natural thing is to Taylor expand this, right? Because we have a function of small coordinates, let's Taylor expand. Okay? So if the displacements from equilibrium are small, from the lattice positions, okay, let's Taylor expand this potential energy, U, which depends now on C vector, okay, about C vector equals 0, if all its elements are 0. Okay? So let's do that. So we're going to write U of these relative coordinates. We just use our normal formula for the Taylor expansion. It depends on these 3n variables. So my first term is just the energy evaluated when all these displacements are 0, right? The second term is I have to take a derivative of this thing with respect to all my 3n coordinates. So I'm going to have 3n terms. I can write that as a sum. So I can write plus sum over I equals 1 to 3n, right? My 3n variables. What I do is I take a derivative of my energy function with respect to each variable. Okay. I evaluate that at the variable set to 0. Right? I evaluate that at c equals 0. And then I multiply it by the coordinate, ci. Right? And since I'm Taylor expanding about c equals 0, I don't need a shift here. Right? I don't need a shift. So that's my 0th order term in the Taylor expansion, first order term. And now I think you can see what the second order term is. We're going to have a 1/2. We're going to have a double sum because I'm going to need to do all possible second derivatives. Right, so I need a sum from I equals 1 to 3n. Now I need a sum from j. And I need all possible second derivatives. So I need d squared u dci dcj evaluated at c equals 0 times c I c j. Okay? That's my second order term plus dot dot dot. Okay? Higher order stuff. Everyone agree with that Taylor expansion? Yeah? What can we, is now, now hopefully it becomes a little bit clear why we did a Taylor expansion. What can we say anything about some of these terms? Can we say anything about this first order term? We're assuming that if the atoms are on the lattice site, that's the equilibrium structure of the crystal. There's no entropy. What's the third law of thermodynamics? Entropy of a crystal at 0 Kelvin is 0. Right? So if we're at equilibrium, the free energy must be a minimum. If the entropy is 0, the energy must be a minimum. Yeah? Okay, so that means if we're at equilibrium at the lattice sites, the energy must be a minimum when you're at the lattice sites. That means this must vanish. Right? This first derivative must vanish if you're at a minimum. Right? So that vanishes. So since this equals 0 corresponds to equilibrium at 0 Kelvin, at 0 Kelvin, this means that these derivatives must vanish. du, dci, evaluated at c equals 0, must be 0 for all ci. Okay, that must be true. So this is going to vanish. Okay, furthermore, this is just a scalar. This is just a number. This is just whatever the electronic energy is when my atoms are at the lattice. I can define my reference energy however I want. It's not going to affect the physics. So I'm just going to define this reference energy to be 0. Okay? There's no loss of generality. No physical behavior depends on your definition of reference energy. Okay? So I can define it however I want. Okay, so furthermore, let's define u of 0 to be 0. This is just my reference energy, my definition of reference energy. Right? I'm just shifting my energy scale by whatever the actual number is. So if I do that, then my energy becomes simple, right? I just have the second order term here. Before I write it down, I'm gonna take one more definition. I'm gonna define what's called the Hessian matrix. Okay, so define, this is called a Hessian matrix. Anyone heard this term before, a Hessian matrix? You hear this in an electronic structure because you calculate the Hessian matrix to calculate vibrations in molecules. Same thing as what we're doing here. And all this is my second derivative. So the element, I'm going to call this matrix K. And so Kij then is just that second derivative. It's defined as this derivative d squared u with respect to dci, dcj, evaluated at 0 displacement. Okay, so that's my definition of K, of the element Kij. What can we say about, is this matrix symmetric? Is Kij equal to Kji? Yes? I see a thumbs up, right? So note that Kij equals Kji because of symmetry of second derivatives. And all of these are real numbers, right? Because my energy is a real number. These things are real numbers. This has to be a real number. So it's not like quantum mechanics where we have matrices that are complex, okay? And so all these are real. Kij are real.
Are they real though?
Yeah. Why not?
I mean, okay, never mind. You can have imaginary. I don't know. I thought the Hessian is where you get like frequencies from and stuff like that, and you can have stuff where you get imaginary frequencies, right? If you're not at minimum.
That's a good question.
That's maybe Dan to get this point, but
If you're at a transition state, yes, but you would have a negative eigenvalue.
yeah,
You'd have negative
values.
curvature, right? So if this thing's negative, right, then it means you're at a transition state, right? And that would give you a negative frequency, because the frequency is the square root of this thing over m. So it would give you imaginary frequency, but this thing itself is real, right? And so, I mean, the simplest way is this is real, this is real, this is real, so it has to be. But that's a good point. Your frequency can be imaginary because your frequency is the square root of this, and this can be negative. So good point. Okay, so that's just a definition, right? So if I make this definition and I use the first derivative vanishes, this definition, then I can write the simple expression that my potential energy, U of these coordinates, is just, I have a 1/2, okay? I'm going to use shorthand for my sum, right? So there I'm putting my sum, I equals 1 to 3n, j equals 1 to 3n. I'm going to use shorthand here, I, j, okay? K, I, j, C, I, C, j. Okay, everyone agree with that? Okay, now we're going to keep putting in matrix algebra definitions because I want to get rid of this sum. I can write this as a matrix multiplication. So now what I'm going to do is I'm going to define a row vector. Okay, this thing is a column vector, and so the transpose of a column vector is a row vector. Okay, so it's just this thing transposes a row vector. So my row vector is C transpose. This is just now C1, C2, dot, 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 C3n, right? So I'm going to define the row vector and a matrix, my Hessian matrix. And
the symmetric, it's a square matrix because it has dimension 3n by 3n. Right, it's 3n by 3n. A matrix, you usually write as bold font in a textbook. I can't write bold font on the board, so use 2 underlines. Okay, so we use 2 underlines to denote a matrix. K, 2 underlines is the matrix, and it's a matrix with elements Kij. Okay, so we know what these elements are, and we just collect all of them in a matrix. Okay, everyone okay with this? So with these definitions, unfortunately I have to erase my pretty picture. Everyone had this burned in their head? Yeah? Take a mental copy of this. Okay. So, the trick now is to see that this is just a matrix multiplication. So, with these definitions, we can write my potential energy expression, which previously was a double sum, now is a very, very simple expression in matrix algebra. It's 1/2 the transpose of that vector, C, times my matrix, K, times my vector, C. Okay, and that's what it is. Okay. Now, depending on how familiar you guys are with matrix algebra, either this being equivalent to this is obvious, or it's not. So, is this obvious? That this is equal to this? Maybe, maybe not. Okay, let's go through it. Let's go through it. So, so what this thing looks like. Okay, so let's consider this. Consider this matrix algebra product. This vector times a matrix times this vector. Okay, what is this? It's a row vector. This is a row vector. It looks like C1, C2, ... C3n. Yeah? This is a square matrix. This square matrix looks like K11, K12, ... K13n. It's a little hard to write. Okay. ... K3n1, ... K3n3n. Right? That's my square matrix. And this is my column vector. C1, C2, ... C3n. Okay? So, to multiply these, you first multiply the matrix by the column vector. A matrix by a column vector gives you a column vector, right? 3n by 3n times 3n by 1 gives you 3n by 1. So this thing becomes a column vector, right? So when I multiply these two, what I get is I get my row vector. It doesn't do anything because I'm not multiplying it yet. And I have a column vector now, because this times is a column vector. But my column vector is, each element of my column vector is a sum. It's this row times this column. All right, so my column vector is now, I have to make it really wide, right? Because the first element is, well, actually I don't. I can just write it as a sum. Let's do that. The first element is a sum right?
Sum over I,
Or right, sum over, let's use j. Sum over j, tell me what,
would it be K, J?
k1j, yeah?
No, okay, yeah, sorry, K1J.
k1j, cj, right? And this is sum over j, k2j, cj, yeah?
Yes.
All the way down to sum over j, k3nj, cj. Okay? So all these elements now are sums. Now, I don't want to go through this again, but now you take your row and you multiply it by a column, and now you get this. Yeah? Okay, so now everyone see that? Okay, great. So basically, whenever you have a row vector, matrix, column vector, it gives you a double sum. Always, always, always. So that's good practice. And the nice thing is we have very condensed notation, right? And so the reason you do matrix algebra is you can condense notation, and as long as you know how to work with matrices, you can do math much easier without carrying around double sums, triple sums, quadruple sums. When you're doing electronic structure and you get 4 index tensors in coupled cluster theory, you want to work with tensors, matrices, okay? So that's why you introduce matrices. Okay, so, what's next? What's next? The kinetic energy. My goal is to work out the Hamiltonian of the system, because if I know the Hamiltonian, then I can solve for the eigenstates, the energy levels, and then I can solve for the partition function. So I'm headed towards the Hamiltonian. I have the potential energy. Now I need the kinetic energy. Okay, so this is my potential energy. So we're halfway done. Okay. Now what about the kinetic energy? Okay, well, let's write the simplest possible expression that we know is true. And we're doing all of this classically. We're going to do it classically, and then we're going to switch to quantum mechanics at the end. It's a bit easier than if we did it with quantum from the beginning. So this is going to be classically, and we're going to switch to quantum at the end. We use T, capital T, for kinetic energy, okay? And in classical mechanics, I can always write my kinetic energy as just a sum of 1/2 mv squared for all my velocities, right? So it's a sum over particles. I'm not going to use I here because I'm using I to denote my 3n degrees of freedom, so I'm going to use alpha for particle, okay? So I'm just going to use an alpha here. Alpha equals 1 to an n, okay? First I'm going to write it in terms of Cartesian, and then we're going to switch to C. Because I have a monatomic crystal, all my masses are the same, right? So I have m over 2. I only have one mass because I only have one type of atom. And then I have Vx squared plus Vy squared plus Vz squared. I'm going to write that as time derivatives. Have people seen the notation where we use a dot for a time derivative? Yes, no, maybe? We're going to introduce it if you haven't. So I'm going to write x alpha dot squared. This is common notation in say, a physics textbook. Plus y alpha dot squared plus z alpha dot squared. Okay? And what this dot means is x alpha dot is defined always. This is always the definition of a dot in physics. It's dx alpha dt, right? Equals v alpha. It's the time derivative of the coordinate. So a lot of times you use a dot. Whenever you see a dot, it's a time derivative. Okay, so everyone agree that that's my kinetic energy? Yeah? Okay, now what we're going to do is note that we want to convert from our Cartesian coordinates to our relative coordinates, because our potential energy is in relative coordinates. And that turns out to be easy. Why? Because if I take a time derivative of one of these relative coordinates, C1, well, Yeah. Okay. What is the time derivative of its relative coordinate? Well, I plug in what the relative coordinate is. C1 is x1 minus x1 naught. Remember, it's a displacement from the lattice position. But this is just a lattice position. This is time independent. Right? So this time derivative vanishes, so I just get dx1 dt. Right? And so the point is, I have a direct one-to-one mapping between the time derivatives of these and the time derivatives of this. So I can just plug these coordinates in for my kinetic energy, right? And so what this means is that, therefore, I can just write T. Now I'm going to change my sum. Instead of doing Cartesian coordinates, instead of alpha denoting particles, I'm going to use I to denote these coordinates. So now I'm going to sum from I equals 1 to 3n, all my relative coordinates, m over 2 c I dot squared. Everyone happy with that? Yeah? Okay.
And so why did you do the partial of x1 minus x naught is equal to just the partial of x1?
Because this thing's constant.
Oh, because it's
Yeah, this is a lattice position, it's not changing, it's just constant. Okay. Now what we're gonna do is introduce more vector matrix notation. Okay? So this sum is actually just a dot product. Right? This is a dot product between the vector ci dot and itself, right? So note that sum over I ci dot squared is just the row vector ci dot transpose times c dot, right? Because this is just the row vector c1 dot c2 dot c3n dot, the row vector times the column vector c1 dot c2 dot c3n dot. Right? So when you take the row vector times the column vector, you get this sum. Right? So I can just replace this sum by this vector product. It's really an inner product. And I can write T in simple notation. T then just becomes m over 2 c dot transpose c dot. Okay. You know, and I've dropped the vector arrows on these C because it's hard to keep my vector arrows and the dots at the same time. But the vectors, it's implied that these are vectors. Okay. So that's my kinetic energy. Okay, everyone happy with this? I have my kinetic energy, I have my potential energy, so now I can write my total energy. Right? So let's write it down. So my total energy this is the energy of what? Well, it's the energy of my atoms moving around in my crystal. So you could call it lattice vibrations. So this is the total energy of my, say, lattice vibrations. Eventually we're going to call it phonons, but now I haven't defined what a phonon is. So we're just going to call it lattice vibrations. Is this, it's E equals kinetic energy plus potential energy. We know what the kinetic energy is. It's m over 2 c dot transpose c dot. We know what the potential energy is, this thing, plus 1/2 C transpose K matrix C. Okay, and I'm dropping my vector arrows because I can't keep the dots in the arrows, so the vectors are implied. Okay, that's what my energy is. So, does this energy expression look like anything you've ever seen before? If you use your imagination, pretend, don't worry about what these coordinates are. If you have a general framework where you don't really care whether it's a Cartesian coordinate or this relative coordinate, and you just say, okay, you have some time derivative of the coordinate squared plus 1/2 times some coordinate times a force constant times the coordinate. It kind of looks like a harmonic oscillator, kind of. Everyone if you use your imagination, it kind of looks like a harmonic oscillator, but there's a problem, right? Because a harmonic oscillator would be 1/2 times a velocity squared plus 1/2 k times a coordinate squared. The problem is that this matrix couples the different variables together because it's not diagonal. So what this actually is, it's a set of coupled harmonic oscillators. Okay, so it turns out to be, this is a Hamiltonian or energy function, right? We're not in quantum mechanics yet, but we know that a Hamiltonian is just an energy function. Okay, for a set, we have 3n variables, right? So for a set of 3n coupled harmonic oscillators, that's the key point. They're all coupled together through this matrix K. Okay? And they're coupled because K is not a diagonal matrix in general, because there's no reason that these derivatives should vanish for I not equal J, right? Right? In general, this matrix K is not diagonal. Okay? And that's why they're coupled. Everyone kind of see that? Yeah? So, we can't solve a system of coupled harmonic oscillators, but we can uncouple them. So it turns out that there's a nice property in matrix algebra that you use in quantum mechanics all the time, where if you have a matrix that looks like this, where it's symmetric, you can diagonalize it. Right? You can always diagonalize a matrix that's symmetric. In quantum mechanics, you call this a Hermitian matrix. And in quantum mechanics, you say you can always diagonalize a Hermitian matrix. So we know in linear algebra, we can diagonalize this matrix. If we diagonalize that matrix, we're essentially doing a coordinate transformation. Whatever coordinates we use to diagonalize that matrix are going to uncouple the Hamiltonian. Okay? So let me just write that down. We know from our linear algebra that we can find a transformation, some transformation to diagonalize. Well, it's a linear transformation, some linear transformation, to diagonalize K. That's just a property. You can prove that in linear algebra because K is symmetric and real. So K is symmetric matrix, right? Kij equals Kji. So we can diagonalize it. If K were diagonal, then this would be uncoupled. And so the corresponding coordinate transformation, okay, this transformation is going to diagonalize K and it's going to transform our coordinates. It's going to be a linear combination of our coordinates. If we can find it, if we can find this transformation, it will give us a set of uncoupled harmonic oscillators because K will be diagonal. Would give us a set of 3n uncoupled harmonic oscillators, which we can solve. Right? So that's the key point here. If we can find this transformation, then we get uncoupled harmonic oscillators. If they're uncoupled, we can solve them because we just solve them one at a time. Right? Everyone agree with that? So the whole point of solving this problem is finding the coordinate transformation that diagonalizes K. So that's what we're going to do. And I might have time to finish that. We'll see. And this is really going to test your knowledge of matrix algebra. Okay. So, this is a really fundamental transformation in physical chemistry. You do this in quantum chemistry all the time, right? You do unitary transformations. So if you're familiar with this, great. If not, it's really good practice. So what we're going to do is we're going to find coordinate transformation. Okay, to diagonalize K. Okay, that's our goal. Okay, we know it exists. We don't know what the matrix is, but we know it exists, right? And so linear algebra tells us, okay, linear algebra tells us that there exists some matrix, which I'm going to call M. Some matrix M, M double underline is a matrix, such that, okay, this is what linear algebra tells you. If we take M and we take its transpose, and we multiply it on the left side of K, and then we multiply M on the right, K becomes diagonal, right? I get some new matrix kappa, and this is my diagonal matrix, okay? Where kappa is diagonal. What I mean, all that means is that kappa ij is just kappa ii times a delta function. Okay, it's just diagonal. Everyone agree with this? That's essentially, this is the linear algebra version of what I just said here, right? That there exists a transformation that diagonalizes K. The transformation is always given by a matrix equation where you multiply some matrix on the right and the transpose of that matrix on the left, right? Linear algebra also tells us something about this matrix M. Does anyone remember? Matrix M has a very, very special property as guaranteed by linear algebra.
So it's the matrix of the eigenvectors of...
Yes, that's right. It will give you the eigenvectors, but in terms of just mathematically, what's the property? The transpose is its inverse. Okay, right? So linear algebra tells us this, and it tells us more than this. And M inverse is its the transpose is the inverse. Okay, guaranteed by linear algebra. Did you guys do this in linear algebra, matrix algebra? Just a long time ago, right? Okay. What this means, if the transpose is its inverse, it means that all the rows and columns are orthogonal to each other, right? Because if you multiply the transpose times the matrix, you're multiplying column times row, basically when you take the transpose, you're flipping the column to the row. So you're essentially multiplying one of the original columns times another of the original columns. And if that's going to be diagonal, then all the columns have to be orthogonal. And so this is called an orthogonal transformation. Okay? This is called an orthogonal transformation. It's called an orthogonal transformation because this matrix has the properties that all the columns are orthogonal to each other. All the rows are orthogonal because of this. Okay? And this is a specific type of a unitary transformation. So in quantum mechanics, you talk about unitary transformations. A unitary transformation is the corresponding transformation if this was complex. The orthogonal transformation is for when the matrix is real. So this is analogous, right, to a unitary transformation in quantum mechanics. Have you guys talked about unitary transformation in quantum mechanics? I know you didn't in the undergrad, but in graduate quantum mechanics, you probably did, right?
Yeah.
Okay. Maybe, hopefully. You know, the only difference here is that we're working with a real matrix. In quantum mechanics, you work with complex matrices. Okay, so we are now in a position to go forward. Let me just write down some properties. Because this is true, I can write down a lot of things. The definition of an inverse of a matrix is if I take the inverse and then multiply it by the matrix on the left, I get 1. I also get 1 if I take the matrix and I multiply it by the inverse on the right, equals, you draw a 1 like that to indicate the unit matrix. So this is a unit matrix, which has the same dimension as this matrix, but 1's on all the diagonals, right? So this is the unit matrix, right? If you multiply a matrix by a matrix, you don't get a scalar. You get a matrix. When I say it's an inverse, it means it gives me the unit matrix, right? So this is the definition of an inverse of a matrix. Because the transpose equals the inverse, I can just plug the transpose in. So it's also true that the transpose times the matrix equals the unit matrix, or the matrix times the transpose equals the unit matrix, right? So these all follow from this fact that it's an orthogonal matrix. Okay. So because it's orthogonal, what I can do is I can take this equation and I can multiply on the left by m. I can multiply on the right by m transpose. This becomes 1. This becomes 1, and I get an m transpose, right? So note that this is equivalent to saying k, I have to be careful with my k's and kappa. This is a k equals m kappa m transpose. Okay, everyone see what I did there? I just multiplied both sides of the equation by m on the left, both sides of the equation by m transpose on the right. 1, 1, 1, 1, and then I get the matrices over there. Okay, so that's actually all the linear algebra I'm going to use. So as long as we're okay with that, we're good. Okay, great. So now what I'm going to do is I'm going to rewrite my Hamiltonian, substituting in these properties. So what we're going to do now is rewrite my energy expression. energy function using this transformation. Okay, so what I'm going to do, I'm going to write my energy. E, where's my energy? Did I erase it? Here we go. Okay, this guy. We're going to rewrite this guy. I have m over 2. Okay. I have my first time derivative E C transpose dot. Now I'm going to do something. Now I'm going to put the unit matrix in between these two. Okay, I'm going to put the unit matrix in between C dot transpose and C dot. I'm going to put a unit, I can always put a unit matrix anywhere I want. But I'm going to use, what form? I'm going to use this form of the unit matrix. Okay? This is the unit matrix, right? So I'm going to insert this in between. I'm going to insert M transpose, right? This is just a unit matrix. So I'm allowed to just stick it in wherever I want. And then I have C dot. Okay. Then I'm going to write this part, the potential energy, and I'm going to substitute K. I'm going to substitute this expression for K. Okay? So I have 1/2 C transpose. I'm going to stick this in for K, so K equals M kappa M transpose. So I have M kappa M transpose C. Okay? Everyone okay with that transformation? Okay, now you're going to learn what phonons are. Okay. Now we're going to define phonons. What phonons are. And you may not be happy with my definition, but this is what they are. Okay? Phonons are this. Okay. Phonons are characterized by a coordinate which I'm going to call eta. Okay? Are defined by some collective coordinate. Right? So phonons are a collective motion of atoms in the lattice. So they're gonna have a coordinate called eta. Okay. This coordinate we need to represent in terms of my 3n Cartesian coordinates, right? So in general, this is a vector because I need to write my phonon coordinate as a linear combination of the coordinates of all my atoms. And now I'm going to define what it is. So eta is defined as M transpose times C. That's what phonons are. Okay, everyone happy with that? So when someone asks you what a phonon is, you write this down.
Yeah.
Okay, that's what you write down. It's a linear, so it's a coordinate. It's a linear combination of Cartesian coordinates, right? C are the atom displacements from the lattice positions. M is some matrix that gives you a linear combination of these, right? Whenever you multiply a vector times a matrix, all you're doing is taking a linear combination of the coordinates. So it says a linear combination, and that linear combination depends on M. M depends on K. Because M is a special matrix that diagonalizes K, right? So coordinates, so phonons are, so the way to think about it is phonons are defined by M, defined by, like John said, this orthogonal transformation matrix is really just a eigenfunction, okay? And the eigenfunction is the phonon coordinate. And M is determined by K, right? Which is determined by K. Right? And so the way you get phonons, suppose, you're doing an experiment on what's your favorite crystal? Gold, FCC.
Gold.
Something boring, right? Or silicon. Take your most boring crystal and you say, what are the phonons? Well, what you have to do is you have to compute K. You have to find the energy, and you have to find the Hessian in the matrix. You can do that with a density functional theory code. So you can download your favorite code from GitHub, right? CP2K or Quantum Express. You download it from GitHub, you run it, it gives you the Hessian. You diagonalize the Hessian using NumPy, SciPy, right? Your favorite Python library to diagonalize a matrix. When you diagonalize it, it gives you M. Okay, so once you go through that procedure, then from M you have the phonons. So you can calculate these things. It requires running a density functional theory code and then just running a linear algebra code to diagonalize it. But in principle, you can calculate these.
Okay, but
And then you can plot them. And then you can download your favorite plotting software and you can plot what this linear combination looks like and see how the atoms are moving together to give you a phonon. That's phonons.
So what's the difference between just like vibrations and phonons? Because I thought
They're the
phonons
same.
were in like a
A phonon is a collective vibration.
Okay.
So here you have vibrations, but they're coupled, right? This looks like a harmonic oscillator. So you could think about these coordinates C as being you could think about the atoms vibrating near their lattice sites, but they're all coupled. So phonon is a special type of collective vibration that's uncoupled from all the other vibrations. Right? So you can use any coordinate system to represent vibrations, but there's only one coordinate system that gives you uncoupled vibrations, and that's the phonons. So that's a good point. Let me write it down, and I'll be done. So phonons are the unique collective oscillations or collective coordinates. There's only one set because there's only one matrix which diagonalizes it. They're the unique collective coordinates that give uncoupled vibrations. That result in uncoupled vibrations. Okay. So you can think of vibrations in whatever coordinate you want, but if you think about them in terms of phonons, your life is easier because then you can think of each vibration independently. Just like you think of vibrations of CO. You think of the symmetric anti-symmetric stretch. You think of water. You think about the symmetric anti-symmetric stretch, the bending. Those are all uncoupled. And so we want an analogous description for crystals that gives you the same picture as uncoupled vibrations in a molecule. Right? So these are the same as a normal mode analysis in a molecule. Let me write it down and I'm done. Okay, analogous to normal modes in a molecule. To normal mode. I mean, that's only helpful if you've heard what a normal mode. Analogous to normal mode description of molecular vibrations. Okay. And just like you can use group theory, everyone remember the group theory? I don't, so don't worry. Just like you can use group theory to tell you what the normal modes are in a molecule, you can use group theory on a crystal to tell you what the phonons are. Because everything has to obey symmetries. Okay. So, okay, sorry I ran over. But now we all know what phonons are, so it was worth it, right? And so next time we'll write our Hamiltonian in terms of these phonons, and then we can solve the partition function. Okay, great. And I'll send an email with our final decision for the exam date.
The final decision for the final.
Right.
And